Day 123 notes pre-calculus. We're going to continue our work with the trigonometric functions, working through chapter 6.2. I've got a series of practice problems that I'd like to work through in this video today. First things first, problem numbers 19 and 20. We need to sketch a triangle that has an acute angle theta and find the other 5 trigonometric ratios of theta. So first thing that I'm going to do is just sketch what a right triangle might look like, and then I'll fill in the information that's given to me. Now, it doesn't make a whole lot of difference where you place your theta at first, but the side lengths that depend upon theta are very important. For example, with the sine of theta, the definition of sine is that sine of theta would be equal to the opposite side length divided by hypotenuse. So we have to get this right. The opposite side length must be 3 and the hypotenuse must be 5. So we have to have that information established based on the definition here. So here's my right angle, and what I like to do is I like to draw an arrow quickly here to demonstrate where the opposite side is. We're always talking about the side opposite of the angle of incidence. So opposite of this angle here is 3, and the hypotenuse of the triangle is here at 5. Now that's pretty good, but we also need this missing side length down here. So let's quickly calculate what that missing side is by using our Pythagorean equation. 3 squared plus this unknown side squared must equal 5 squared. So that's 9 plus b squared equals 25. B squared is equal to 16. Therefore, b itself has to be 4. So once I have all 3 of my sides of the triangle, filling in the trigonometric ratios is really easy. Sine of theta we know is 3/5, so immediately we should know that cosecant of theta is equal to 5/3. These are inverses of one another. Cosine of theta would be equal to the adjacent side divided by the hypotenuse. Now here's my opposite side again. So we know that 5 is the hypotenuse because it's the longest side of the triangle. That means that 4 has to be the length of the adjacent side. And that is true. It is the side closest to this angle, but it's not the hypotenuse. So we'll write cosine of theta is equal to 4/5. Secant of theta is the inverse of that, so we just have to flip this fraction. And lastly, tangent. Tangent of theta must be the opposite side, 3, divided by the adjacent, 3 divided by 4, by definition. And therefore the cotangent, which is the inverse of this, would be that same fraction just flipped over. And there we have our 5 additional trigonometric ratios. Let's do the same for number 20 here. We'll draw another right triangle, and again I'll put theta down here at the bottom right hand corner. Doesn't matter if we place it here or if we wrote it up here in this corner, we can still create the right triangle appropriately. Now the opposite side would be this one across from this angle, and I don't need the opposite here because I'm dealing with cosine. Cosine relies on the adjacent side divided by the hypotenuse. So the hypotenuse here is 40, the adjacent side is 9. We can use a quick Pythagorean equation to find this missing side over here. So a squared plus 9 squared is equal to 40 squared. That means that a squared plus 81 is equal to 1600. Therefore, a squared itself must be 1600 minus 81. That to me looks like it's 1519. So then a must be the square root of 1519. Now I'll go to the calculator here to see if that can be reduced at all. I'm not sure if it can, so I'll enter the square root of 1519. Oops. Let's get back inside here. 1519 Okay, so that does reduce. We'll call this 7 times the square root of 31. That'll take up a little bit less space. And it's helpful to have the reduced radical whenever possible. So we used the Pythagorean equation to simplify these data points. We can now find the rest of our functions. I should say our ratios. Let's start with cosine of theta, since that was given to us. That was 9 over 40. Therefore, secant of theta must be 40 divided by 9, since those two are inverses of one another. Sine of theta is equal to opposite divided by hypotenuse. So we'll call this 7 times the square root of 31 divided by 40. Therefore, the cosecant of theta must be equal to 40 divided by 7 times the square root of 31. Now, if you write this answer and you compare it to one that you might see in the back of your textbook, you might see that they take this a step further and they rationalize the denominator. Or in other words, they do some math to get rid of the square root in the denominator. Traditionally, we would like to do that. However, at this point in the class, I'm not going to be too concerned with us rationalizing the denominator, and we'll leave this answer as it is. We'll encounter that also with tangent and cotangent. Since tangent is defined as opposite divided by adjacent, we would have 7 times the square root of 31 divided by 9, and cotangent would be the inverse of that, which is 9 divided by 7 times the square root of 31. Again, we're not going to bother rationalizing the denominator. We'll leave these answers as they are. For number 31 through 38 in our practice in the textbook, we're being asked to solve the right triangle. And what that means is to find all missing sides, find missing side lengths, and angle measures. For me, it's easier to find the angle measures first, since I know that all three of these angles must add up to 180, and 90 of those degrees are associated here with this right angle. I know that 90 minus this number here would give me the other angle, so that one has to be 45. And in this case, we have to have an angle of 15 degrees, since 15 and 75 must add up to 90. So that takes care of our angle measures. Let's work now on finding our missing sides. In number 31 here, according to our original angle, this side over here is our opposite side. And we can use it to find this missing side if we'd like, and we can also use it to find this missing side as well. So I'll call those X and Y here. Now I know that when I'm dealing with an opposite side and a hypotenuse, I can either use the sine function or I can use the cosecant function. Now if I use the sine function, that means sine 45 has to equal 16 divided by x, because sine of some angle is equal to the opposite side divided by the hypotenuse. If I use the cosecant function, we can still find cosecant of the same angle measure, 45 in this case, and that must be equal to x divided by 16. Now it really makes no difference which one you use, the end result would be exactly the same. However, the algebra used to get there might look a little bit different. For example, solving for x using sine requires us to put the sine of 45 beneath 16 in a fraction, whereas when using cosecant, that would be 16 times cosecant of 45 degrees. And if I jump over to the calculator so that you can see that, I'll first begin with the fraction 16 divided by sine of 45 degrees, and I'll press enter, and that's 16 times the square root of 2, or in other words 22.6274. X is equal to 22.6274. Let's check this calculation. 16 times cosecant of 45. So 16 times cosecant of 45. There's that 16 square root 2 again, and the decimal result is exactly the same as well. x is equal to 22.6274. And either solution, as you can tell, is correct. Either approach is perfectly fine. Now that solves for x. We can also set up an equation to solve for y. Now this time I'm going to recognize that this is an adjacent side. So we have an adjacent side and an opposite. So the rules that work with adjacent and opposite sides are tangent and cotangent. This time tangent of 45 would be equal to 16 divided by y, or you could try cotangent of 45 is equal to y over 16. I'm going to pause the video and I encourage you to do the same to solve for y here and see if you get the same result as me. And in both cases you see that y came out to be 16. Either approach would have been perfectly fine. Now, hopefully you would recognize that 16 is the correct solution because we have an isosceles right triangle here. If the two angles are the same, then therefore the two side lengths must be the same. If this is 16, then this must be 16 as well. So this is good. We've got the triangle now solved. We found a missing angle, 45 degrees. We have our two missing sides, x and y. So if we were to summarize that, maybe I would write that in just a little summary block over here off to the side. We would say side length x is equal to 22.6274. We found that y is equal to 16, and I'm going to call this missing angle theta. Since we use Greek letters usually for angle measures, we found that to be 45 degrees. And that would be a good place to write our summary statistics. Those are the three pieces that we needed to find in order to solve this triangle. I recommend that you practice number 32 on your own. I'm going to pause the video and fill in the work. I think you can use this as a guide over here on the left-hand side to solve for, well, we've already got our missing angle, but you can now solve for missing side length x and our missing side length y. So let's see what you can come up with. And here we go with the solution. I used the same functions, sine and tangent, to calculate my missing x and y value. And from a moment ago, we recognized that theta was equal to 15. Now, it's okay to name these side lengths and angle measures anything you'd like. For example, we could use the letter A or B for either of these sides. You can even use C or D, whatever, any regular letter would work here. When we're talking about angle measures, if theta has already been used, you can use others that we've seen so far this week, such as alpha and beta. And you can use either of those options for angle measures as you label them in the future. Here's number 35. We can use this information to solve the triangle as well. So I'm going to look for side length A, side length B, and angle, I'll call it alpha this time. I'll pause the video again and let you try working on this as well. In just a moment you can check your answers. And actually I just realized something. We haven't discussed triangle angle measures that are given to us in radians rather than degrees. So hopefully you didn't spend a lot of time practicing that. We'll actually skip this one because of our angle measure here given to us in radians. Measuring angles in radians or degrees is kind of like measuring between degrees Fahrenheit and degrees Celsius. They both measure the same object, just done with a different scale. So we haven't talked much about those radians, if at all. So we'll just skip those types of problems for this week. Now with number 41 here and number 43 in just a moment, what we have are pairs of triangles that are kind of connected, and our objective is to find a value for x, but this time, this value of x is not just associated with a single side length. For example, here we have x that's associated with side length A and side length B here. If I call those A and B, I could add A and B together if I can find each of those, and that would be my total length for x. So I'm going to write that off to the side, and that gives me something to work towards. Now, if I look at the triangles that I'm left with, for example, this triangle on the right-hand side, I can decide if I have enough information to solve for side length A. And I think I do, because based on this angle measure here, I have an opposite side and an adjacent side. So if I use tangent or cotangent, I can work with the angle measure 30. I can work with the angle measure 30 here and these two side lengths to create a ratio. So I have 100 divided by x. X would have to be equal to 100 divided by tangent of 30, and oops, not x. I shouldn't use the letter x here. That represents my total target. I should be using the letter a here. So a is equal to 100 divided by the tangent of 30. So we have 100 divided by the tangent of 30, and that comes out to be 173.2051. 173.2051. Okay, so we have A now. We can also find B, I believe, because now we have an opposite side and again an adjacent side. We can use tangent again. I'm going to use cotangent though, just to get the extra practice. Cotangent of 30 degrees must be equal to, instead of opposite over adjacent, this would be adjacent over opposite side. So we'll have B over 100. This means that B is equal to 100 times the cotangent of 30. So when I go to the calculator here, 100 times the cotangent of 30. And that's not going to work. Of course, that's not going to work because I used the wrong angle measure here. It shouldn't be cotangent of 30, it's cotangent of 60 this time. We're dealing with a different angle measure in a different triangle. So let me fix that and recalculate. So that's 57.735. 57.735. And I do need to correct this. I want to make sure that I have all of my notes correct as well. It's cotangent of 60, this angle measure here, not 30 from our original calculation. There I did. I almost did it again. It's cotangent of 60. There we go. And so now that we've identified what A and B both are, we can add those together to find X. So we have 173.2051 plus 57.735, and that totals 230.9401. 230.9401. That's the total length for side X. Let's see if we can work through number 43. I'll give you some pointers here and let you work on this one on your own. We have an unknown side length x here that needs to be solved. We need to find x, but we have a right triangle in this position here with an angle measure, and an opposite side. We might be able to use this opposite side and the hypotenuse, use this opposite side to find our hypotenuse, and then that hypotenuse becomes the opposite side of our next triangle with 65 degrees. So 65 degrees and this opposite side, which was the hypotenuse of our previous triangle, would allow us to find the hypotenuse of the final triangle over here, which would be letter X. So it looks like we could use the sine rule or cosecant rule here, because that'll deal with opposite and the hypotenuse. And then we can use sine or cosecant again here, because that will work with the opposite side and hypotenuse as well. So I encourage you to pause the video and try solving this on your own, see what you can do to isolate X by itself. I'll come back in just a moment with a solution. And here we go with a solution. I used sine first. Sine of 60 degrees would be equal to 50 divided by h. That would be our opposite side divided by the hypotenuse. Once I calculated what h was, I then used that as my new opposite side, and I used the cosecant rule this time, even though I very well could have used sine again, but I chose to use cosecant this time. Cosecant of 65 must be equal to the hypotenuse x divided by the opposite side length, which was the 57.7350. When solved for x, I see the result comes out to be 63.7035. So it's important to remember here that the measurements x, this 50, and this h are all measurements of length, like inches or feet or something like that. This represents the length of an object, whereas the 60 degrees and 65 degrees represents the angle measure. It's kind of interesting that the results here, 57 and 63, were so close to these other angle measures. I just wanted to remind you of that so that you don't get them confused with between angle measures and side lengths. I hope that helps understanding how we can use these trigonometric ratios to solve some problems. Please let me know if you have any questions tomorrow in class.